Oh, here we go, into alternating series error. You'll sometimes hear that called the upper bound of error of an alternating series, or the remainder, the remaining amount. What is this all about? Well, we're going to talk about just first what error is. Then we'll talk about what the alternating series error is and how it's actually really simple to find. And we'll cap off this video with the idea of why the error comes from, well, where it comes from. So we're told here that the error of the amount, or the amount of a finite approximation of an alternating series is off by, is at most, okay, that sounds really confusing. Let me just kind of break that down. The error is the amount that you're off by with anything. Let's just take a real world example, for instance. Let's say that we measure my height to be, and you can't tell from the computer, but I'm about 6 foot even, with an error of, let's say, plus or minus 1/4 of an inch. That means that I could be 6 foot and 1/4 of an inch, 6 foot minus that 1/4 of an inch, or anywhere in between. So that's where my error is bounded. Those are the boundaries of the error. So if we add up an infinitely long alternating series like this, and we want to figure out, well, what's the approximation like to the fifth term? 1, 2, 3, 4, 5. We go out to the fifth term and we get an approximation of this infinite sum. We want to know, well, how far off are we from the actual sum? And while we can't find the exact error, we can say, well, we're off by at most this much, which gives us an idea of how accurate our approximation is. It's pretty valuable. So overall, the error of any alternating series is the absolute value of the first unused or ignored term. So in this case, if we wanted to find the upper bound of error of the first 4 terms, being used to approximate this infinite sum. So let's say that your approximation was this amount right here. You add these values up, whatever it is, 1 minus 1/3 plus 1/5 minus 1/7, and then you add 1/9 onto it. Well, this is the first 4 terms. They're used to approximate that infinite sum, whatever that number is. Then we want to know how much are we off by. So the upper bound of error is at most, and here's how we would write it. So you could write it, I've seen it written this way. That means the remaining amount that we've yet to add on after the first 4 terms. You could also write that as the true sum, right? So that's the sum out to infinity, or just s, minus s sub 4. That would be the difference between the exact sum and the approximation. That's what error is, right? Your approximation subtracted from the exact amount that you have. And what will that be? Well, that's going to be less than or equal to the absolute value of the first ignored term, which is, in this case, the absolute value of 1/9, or 1/9. So what that means is, whatever the sum is, we're off by at most 1/9. Maybe we're off by only 1/100th. We don't know. But that is the farthest off that we can be off by. And we'll go over why that makes sense towards the end of this video. And again, I go over some notation here. You might see error in absolute value equals the remainder in absolute value is less than or equal to the absolute value of the ignored term. Some textbooks have it this way. This is the actual sum minus the approximation in absolute value, because we don't know if we're off on the positive or negative side of things. Maybe my height in that analogy was off by plus 1/4 or off by minus 1/4. The absolute value says the size by which we could be off could be plus or minus that amount. That's equal to the remaining amount. So the remaining amount, the remainder is the error. It's how much remains left in that sum is at most 1/9. And that's what this says here, is less than or equal to the n plus first term. So in this case, we use the first 4 terms. The n plus first term would be the 5th term. And a little bit of grammar action there, which I'll correct for the notes on you. Sorry about the little grammar problem there. It happens from time to time. Okay, let's keep rocking and rolling. Let's use it. This says find the 5th partial sum. So let's do that. So we're going to find the 5th partial sum of this thing. Well, to do that, let's just kind of expand it out. If we expand this thing out, we're going to get -1 to the 1 is -1 over 1. And then that's going to be plus 1/2, and then minus 1/3, and then plus 1/4, and then minus 1/5. That is your 5th partial sum. So quite literally, your 5th partial sum is the sum of the first 5 terms. So remember your partial sums. If you're a Harry Potter fan, I don't mean to say parcel tongues, it's partial sums. Anyway, nerd joke. Find the upper bound of the error if this partial sum, this thing, is used to approximate the infinite sum. Well, okay, remember that the error is the difference between the true sum, which is s, right? And you could even do this if you want to be really fancy. You could say that's the true sum, which is n equals 1. to infinity of negative 1 to the n all over n. That's the true sum minus the partial sum out to the first 5 terms. That is the actual error. That will be less than or equal to the absolute value of the first ignored term. Okay, so that'd be the absolute value of, well, the first unused term would be 1/6. So we are off by at most 1/6 for plus or minus of whatever the true sum is. Now, if you had to justify this formally, here's what I would say. You have to first prove that this is an alternating series that converges. So I'd say since the alternating series has terms that decrease in absolute value to 0. So has terms, I want to state that very formally, that decrease in absolute, I'll do DECR for decrease, that decrease in absolute value, abs value, don't you dare abbreviate on your test, in absolute value to 0, it converges. And then we say, therefore, the error is at most the first ignored term. So therefore, the error is at most the absolute value of the first ignored term. The absolute value of the first ignored term, or first unused term, or 1/6. So that's how you really formally state it. You actually have to show that the series converges. State that it's alternating, because that then allows you to use this logic, and then you state, therefore, it's the first unused term that is the upper bound of the error. Okay, now, how do we figure out our approximation? So determine the interval over which the exact sum is bounded, meaning I want to know between what two numbers this thing is bounded. So if you think about it, we take our approximation, and that's plus or minus the error. That's how error works. Again, I'm going to go back to what I talked about in the beginning of the video. We approximate my height as 6 feet. We're off by upwards of 1/4 inch, and at the very most by minus 1/4 inch. So we're somewhere between 6 minus 1/4 inch and 6 plus 1/4 inch. That's this exact idea here. So what I'm going to do is I'm going to pause the video. I'm going to calculate this as a fraction, and then we're going to calculate the interval over which this sum is bounded. And through some very shoddy editing there, what we're going to get here is that this is actually equal to negative 47/60. That's our approximation of this entire sum. So this thing keeps going on and on and on and on until we get to negative 1 to the nth over n, and it keeps going on and on and on and on. And we're saying that the approximation is approximately negative 47/60. So since our error is at most 1/6 in either direction, that means that the negative 47/60 minus, now it's going to be 1/6, is less than or equal to the true sum. Sometimes people will use S. I'm just going to use the summation notation. So the true sum is the exact infinite summation, like that, which is less than or equal to the approximation plus the amount that we're off by. So it could be plus or minus that amount. And then when you simplify that down, this is 10/60. So that would be negative 57/60, which is less than or equal to that true value, not talking about the hardware store, which is, that's a terrible joke, which is less than or equal to, we'll add 10/60 on top of that, which is negative 37/60. So what this means is the actual sum, the infinite sum, is somewhere between roughly negative 1 and not quite negative 1/2, which makes sense. We start out with a negative 1, we add a 1/2, so there we're at negative 1/2. And then we add another negative 1/3, and every fraction is going to chip off a little bit less than what the previous one put on, right? But it's going to alternate. So eventually it's going to stabilize between that negative 1 that we started with and that 1/2 that we added on there. Makes a ton of awesome sense. I love it. I love it. So that's it. That's the idea. The question becomes, though, why is it the first ignored term? Why is that our error? So we're going to take a look at the alternating series, the alternating harmonic series that we know converges. The harmonic series itself diverges. We're going to expand that out. So if we take a look at this thing, we would get negative 1 plus 1/2 minus 1/3 plus 1/4 minus 1/5. So this is, again, basically that last series that we just took a look at, right? That exact same series. So we already know the numbers, but why did it make sense that the error was at most 1/6? in either direction. So we're going to use those vectors again that I used in video 2. If you haven't seen that, you got to check it out. It's a good watch. Has to do with why the alternating series works. That size of that right there is your -1. That's the first term and the direction in which it's going to the left. Then we're going to add 1/2. So I'm going to go to the right and we're going to go to about 1/2, just about. Right? And so now we're at 1/2 itself. And then we're going to subtract 1/3. It's just an approximation, roughly that. I could be wrong with how long that should be, but that works. And then we're going to add 1/4. And then we're going to subtract 1/5. Now, what you're seeing here, I hope, is that with each value that we add or subtract, we're getting almost into like this pyramid shape, where the amount that we're adding or subtracting is less than the amount before. And so what you can see here is the next term, that 1/6 is going to be the error. I'll put that in orange. That is going to enclose all successive amounts. Just like all the successive amounts after -1 were all housed within it because we kept alternating with lesser and lesser values. So this is that 1/6 value. The next value will be -1/7, and then 1/8, and then 1/9. They're all housed within the 1/6, meaning the most amount that we're going to be off by, for sure, is 1/6 because every other value is within it. Isn't that cool? And it works that way with every kind of alternating series that converges. It's got to be a converging alternating series. And so if you wanted better error, go out to more terms. Go out to the 500th term, and then 1/501st. 1/501 would be at most the error. So it really just depends how far out you want to go to get the smaller and smaller error. Isn't that cool? I think it's really, really rad. All right, enough of my opinion on how rad this is. I'll see you in the next video. Conditional and absolute convergence is on the docket. It's going to be great. Peace.